All right, welcome to video 121 on aircraft control surfaces and components. So here, this is a little bit of fundamental vocabulary, but also we're starting our discussion of a lot of different airplanes. And one of the things that I want to get you to think about through the course of this class is how every airplane is really the same, even though they're all totally different. So this is the original Wright brothers flyer back from the early 1900s. This is an F-35 Lightning II, but they still have many things in common in terms of the way that they're built, despite also being totally different. So the idea is that all aircraft have common structural and control components. All aircraft have fundamentally the same parts that do fundamentally the same things. And so the question that you should always ask yourself when you see two aircraft that look so different is, why do they look so different? What is it about their job? What is it about the way that they were built? What is it about the time and place and materials? What is it about them that makes them different? Because it's not just a lark, right? Aerospace is a very exacting field. Nobody builds something a certain way just for fun. They build it that way because that's the way it has to be built. So starting at the most broad, the high level, there's kind of 5 different sections. You know, the wing. Wings are important on an aircraft. They're what make you fly. You've got usually some kind of power plant, or do you? Sometimes you can have gliders that have no power plant. You have landing gear, but also sometimes you don't. You have a fuselage, mostly, which is what the wings connect to, and it holds the people and all the things. And you have the empennage, colloquially known sometimes as the tail. We will try to use the empennage because it's a better vocabulary. And again, you might notice, and we'll get to this when we talk about history, a bunch of French words popping up here and there. See if you can spot them. On that empennage, zooming in on the empennage, we have a bunch of different control surfaces. So on the back, we have the horizontal stabilizer. The horizontal stabilizer is this whole horizontal part, and the horizontal stabilizer is typically fixed, and it's meant to stabilize the aircraft. You also have attached to it a flexi part called the elevators, and the elevators go like this. So here's the horizontal stabilizer, and the elevators are kind of free to move up and down in the back, and we'll talk about exactly what they do and which way they move. The vertical stabilizer is here with a rudder attached to it. You've got on the wing 2 different control surfaces. It's a little hard to see here, but on the wing you've got a set of control surfaces on the inboard side near the body. Those are the flaps. And on the outboard side near the wingtips are the ailerons. Don't get them confused. They are very different. Flaps only go down, for instance. Ailerons can go up and down. Here's another little view of the tail, just a different plane, and just goes to show it is a very similar structure: vertical stabilizer, horizontal stabilizer, elevators, and rudder. In this case, we also have a little something called a trim tab. A trim tab is kind of like a permanent little setting you can dial in. Imagine you're at the grocery store, right, and you have a shopping cart, and the shopping cart always veers to the right. Well, that's kind of annoying because you always have to push it to the left. A trim tab is like a little thing you can dial in to say, well, I just want a tiny bit of left push. It helps you adjust for wind and other things so that your plane keeps flying in a straight line all the time. Here's just another plane: fuselage, cockpit, power plant, etc. Just showing you again how every plane, even if they look very different — here's a Coast Guard plane, has fundamentally the same components. Here's a little model plane with all the same components. Here's a little cutaway of the fuselage, and you'll notice that it's built of all these little triangular sections. If you built your little bridge in IED or whatever, you'll remember that these triangles are very strong, as well as being very light. The fuselage is empty. Weight is our enemy in this. Similarly, wings are often hollow. Here they're built with what's in this plane. You can see a rib and spar construction, which means you'll get these little ribs that will hold the shape of the wing, and then they're connected together. So here's a rib, and they're connected together. Multiple ribs are connected with these spars that run all the way down the wing. This one has a little wing strut for support to keep the wings from flexing too much. Winglets, we're not going to talk about the function of winglets today, except insofar as they increase the efficiency of the wing a lot. And so, especially on planes that care about efficiency, like passenger aircraft, you will see them all the time. Planes that don't care that as much about efficiency, like fighter planes and small recreational planes sometimes won't have winglets because they're not looking to eke every little drop of fuel out. You probably all know about center of gravity. That's where an aircraft is balanced. Center of gravity is going to be really important when we discuss aircraft because it gets into the idea of stability. We need to control an aircraft to be stable. If it hits some turbulence or some bumpy wind, we want it to come back to where it was. And there is a fundamental trade-off that you need to get into with this, which is stability versus maneuverability. Some planes are very, very stable and are not very maneuverable. Military planes tend to be very maneuverable, but not very stable, and we'll talk about that. Yeah. So we could need some more vocabulary now to talk about how our aircraft moves. Now, I can't just really use X, Y, and Z coordinates to talk about where a plane is and which way it's pointing, because at any given moment it could be in a certain place pointing in some different direction. So what instead we do is we run a set of axes. Instead of X, Y, and Z, we run a set of axes through the plane. We have 3 axes. One that goes along the plane from nose to tail, called the longitudinal axis, and I remember that it goes along the plane. The lateral axis runs through the center of gravity sideways, and the vertical axis impales the plane vertically and moves that way. And each one of these axes has a name for the kind of motion around it. You need to be able to control yourself in all these types of motion. So movement about the longitudinal axis is called roll. You're going to roll left or roll right, and that is controlled by, that is controlled by the ailerons, which I misspelled. That is controlled by the ailerons. Pitch is controlled by the elevators, and yaw is controlled by the rudder. Now the real question is, how do you have to move them? So let's start with pitch. Let's say I want to pitch the nose of my plane up so that I can climb. I want to climb up into the air. Well, which way do I have to move the elevators to do that? So I'm going to sketch an image of the plane. Here's the whole fuselage of the plane. And here's my elevators. And let's say I put my elevators down, just for the sake of argument. Just for the sake of argument, I put my elevators down. In this case, let's look at what happens with the airflow. The air comes in and is pushed down by the elevator being down. And what that does is it pushes the tail up. Now you might think, and this is a very reasonable thing to think, you might think that that would make the plane go up. But what I want to encourage you to think of is that a plane is a giant seesaw. And what's going to happen is the plane is actually going to rotate around its center of gravity. So what happens is when the tail gets pushed up, the nose gets pushed down. So the net result is elevator down equals nose down. And similarly, if I put the elevators up instead, well, if the elevator goes up, then my air is pushed upwards. Let's do this in a slightly different color instead. So let's say I put my elevators up, then the air gets pushed up, my tail goes down, and my nose goes up. So the net result, again, in the end, is elevators up, nose up. This is going to take some getting used to. Similarly, for yaw, if I want to move left or right, we can kind of draw a top view of my plane. So if I move the rudder, in this case, to the left, my air gets deflected to the left, which pushes my tail right, and my nose left. So after all of those little mental gymnastics, the comfortable thing here is that we end up with rudder left equals nose left, and rudder right is nose right. Ailerons are a little bit more complicated because you have to think about the way that you want your plane to roll. So let's say I want to roll left. Roll left. Then what do I need to do? I need my left wing down. And my right wing up. Well, how do I make my left wing go down? That means I have to, if I want to roll left, I have to raise the left aileron. So left aileron goes up, air goes up, left wing goes down, and lower the right aileron. I really suggest you make airplane arms. Stick your arms out at the side, imagine which way they'd be going. Again, here, just to roll left, the right wing has to raise and the left wing must descend. So the right aileron is raised and the right aileron is lowered and the left aileron is raised. So that, again, on the right side, air gets forced down, forcing the wing up. So right wing goes up. On the left side, air gets forced up, which pushes the left wing down. There are, of course, pilot controls that you have to use on this. For the yoke, if you want to rotate it left, if you want to turn left, you rotate the yoke left. If you want to turn it right, you rotate the yoke right. Pitch, lowering the elevator, pushes the nose down. That's pushing forward, and to climb, you pull up, pull up, pull up, pull up. Rudder is the same way. To nose left, rudder has to go left, and usually there's foot pedals for that. So this is a table that you should really memorize or put in your notes. It's a really good table. It's going to serve you extremely well. So just to finish up our discussion here, let's look at some different airplanes and see why and how they have different characteristics. So the differences, again, are never just aesthetic, even if they're pretty paint jobs. The question is, why were they built that way? So, for instance, we've got planes with different wing configurations, a high wing, a wing in the middle of the aircraft, or a wing at the bottom of the fuselage. A high wing generates a lot of lift because the airflow over the top of the wing is uninterrupted. You get a lot of downward visibility, so you'll see a lot of reconnaissance planes and things with a high wing. Its best feature is that the center of gravity is really high. You can kind of think of the plane as hanging off the wing. So if you kind of think about it, if the plane is disturbed, it's going to, like a pendulum, kind of come back to normal. So they're extremely stable. So you'll see a lot of Cessnas and stuff like this. The pusher engine is a little unique and different from the high wing. So high wing's extremely stable is the main message. Mid-wing, I don't know why you would use a mid-wing because it doesn't generate as much lift. And it also impacts fuselage space because the spars for the wing run straight into the fuselage. I guess it's kind of sporty looking, but gives you some good maneuverability, but isn't that great. Low wings are kind of right in the middle. What they do get you is a lot of what's called ground effect. So you basically get air reflected off the ground, which increases your lift when you're right close to the ground. So you can get shorter takeoffs and landings. It does limit your downward visibility somewhat, although if you're a military plane, it also protects you, your wing protects you. It also is kind of like an upside down pendulum. The wing is on the bottom, so which makes the plane less stable, which actually coincidentally makes it a lot more maneuverable. Your wing configurations, you can have, different things. So you could have, you see a lot of biplanes and even triplanes. Why did we do this? Well, basically the engines were really bad back in the day. They didn't have strong enough engines to reliably get off the ground with just one wing, so they thought 2 wings, more lift, double the lift. The problem is you also get a lot more drag, not just from the wing area, but all of these struts and cables and stuff that have to bind the wings together. So you don't really see many biplanes these days. Canard wings, you get a lot of maneuverability because you've got your wing surface far away from your center of gravity. So you get a lot of maneuverability, but they can also be a little unstable. And they tend to be, a little bit more maneuverable, sometimes in a tough way. You can have different configurations of vertical stabilizers. This one has 2 vertical stabilizers. to improve yaw control. You'll note maybe this plane needs more yaw control. There's also a giant engine in the middle, so splitting the tail might have been a design consideration to make room for the engine. This one has lots of vertical stabilizers, and look at the size of this huge honkin' rudder. It's like 2/3 of the whole thing. So this thing must need a lot of stability, a lot of yaw control. This one's interesting, a V-tail. This one kind of doesn't have vertical and horizontal stabilizers. It has a mix of both. And what you actually find is that these things in the back are neither elevators nor rudders. They are a combination. They are called ruddervators. And they actually move in pairs. If you move both ruddervators up, it's like putting the elevators up, because they kind of will push this way and that way, the two lift vectors. Both down is like elevators down. And then if you move those ruddervators in mismatched pairs, it'll give you left and right rudder. So the V-tails are kind of neat. You can have different power plants. We won't really get too much into this, but they all have their advantages and disadvantages. Here's a tractor, because it's in front, it pulls the plane along. You'll notice that there's no covering on the engine. That's because it's cooled by air. A pusher's in the back, which tends to not foul the air over the wings quite as much, but the engine doesn't get... So this one has the advantage that the propeller gets nice clean air for maximum efficiency, but the wings get kind of dirty, turbulent air from the propeller. So less wing efficiency, more engine efficiency. This is the opposite. You've got some jets that can vector their thrust and like hover and different things like that, which is kind of neat. You have different kinds of struts. Again, this isn't a main part of the class, but again, the whole point of this is that they're all a little different. You have floats if you want to land on water, if you're taking off from a runway or other things. You may need different amounts of gears. If you're landing on a hard field, you have these giant beefy shock absorbers and a lot of ground clearance. Look at all this ground clearance. If you're on a soft field like sand or something, you need big soft tires to get a grip. You can have things of different sizes. C5s are gargantuan. You can hold like entire tanks in these. There's some people for scale. And then you have some weird specialty aircraft. So this is the 747 that was configured to carry the old space shuttle. You'll notice the enormous winglets and oversized tail and things like that. So tons and tons and tons of extra features to improve stability with this huge heavy load. So I know this is pretty quick, but you can go back through it if you need to. We're going to talk more in class about how to get that kind of, how to control all of your control surfaces by using paper airplanes.